Okay.
Thank you.
The point.
Oh, this is the point. Okay. You can hear me, right? Perfect.
You introduce it.
Okay. Yeah.
Can we start? Afternoon second session's talk is Professor Giorgio Torrieri. What?
Giorgio Torrieri.
Giorgio Torrieri. His talk, title of the talk was changed. And please introduce yourself.
Yeah. Okay. Hi. Yeah. Thank you very much for Bruno and the other organizers for their hospitality. Sorry for any particular audience member who wanted to hear about the title which was written there, which had to do with hydrodynamics. I simply decided, I've asked around for the audience, and I simply decided that for this audience here who is interested in ferret knot, this topic would be this topic which brings back a more innocent time when I was young and naive and wrote PRLs, will be more appropriate. It is something I worked on for a long time ago, but there is, as you will see, lots of unsolved questions, so I would like to revive this topic. Quarkyonic, just out of interest, so if you have never heard of this word, can you raise your hand, please? If you don't know what Quarkyonic matter is, shut up, I know you. I know you know. If you've never heard of this word, please raise your hand. Thank you. So the rest of you at least have vaguely heard about it, right? Okay, no problem. Even better. So I'm going to explain what this is. This is based on a very interesting paper back from 2007 by Larry McLaren and Rob Pizarski. I'm going to ask whether it exists, and the answer is I have no idea. And therefore, I'm going to propose some ways to look for it in experiment, because experimentalists always need something fun to do. The basic idea is that, just to introduce things a little bit, most of our community is focused on the LHC. However, I don't need to tell you guys this, there is this very exciting low energy program going on as well, I mean, of which the biggest chunk is FAIR. What is the point of it? The point is that there is a correlation between quality of experiments and energy that kind of needs to be broken. People go to higher energies and they build better experiments because of progress. And this basically means that certain observables at lower energies, which are a bit more complicated, you miss them because your experiment at the lower energy was less developed than the experiment at the higher energy. And maybe if you're looking for the next new beyond the standard model particle, that's okay. But if you're looking for collective phenomena, that's not okay, because it's not really true that you will have more physics at higher energy. In fact, the idea is to explore higher chemical potential, where hopefully you will find lots of new and interesting stuff like a critical point. The only problem is that this thing here looks like drunk people playing on a dartboard. In fact, it's theorists predicting where the critical point is. And every little model gives you wildly different results. Huh?
That plot should not be shown anymore. I mean, this is just nonsense. I'm sorry.
Okay. Fair enough.
Do we have an answer for the critical point, the location of the critical point? I don't think we do. I don't think there's a definite answer.
I will present one tomorrow. It's not definite, but this is much more solid than any point on this plot.
Yeah. But
still
kind of an agreement in the theoretical community on that, not to show that.
well, I will just say that in addition, there is one point there there is one extra point on this diagram which is colored white, which is there is no critical point. There is at least one lattice collaboration which has serious doubts on whether there is a critical point or not. So maybe there is nothing. Why is this? Because a bunch of effective theories all fail when the chemical potential becomes of the order of the temperature. There is the two-dimension full scales are about the same, and therefore you cannot do scale separation. Lattice QCD also fails. ADS-CFT, let's not even waste our time talking about it. Sorry. Well, no, ADS-CFT is based around NC equals infinity, so I'll spend most of my talk talking about it. All I'm saying is, one, experiments are actually really good because theorists have no idea what to look for, and there might be surprises, and indeed, theorists who work in this regime let your imagination flow. There is all kinds of speculations about non-trivial structures completely absent from the high temperature regime, which one can find at finite chemical potential. One particularly interesting one, which is particularly interesting just because how conceptually sort of easy and rich it is this thing called quarkyonic matter. The idea is very, very simple. Go to a chemical potential of the order of, the baryochemical potential is of the order of the baryon mass. What this means physically is that there is one baryon per baryon. There is one baryon per baryonic volume. Baryons form a system of tightly packed spheres. And now, take the number of colors to infinity. Take the large NC approximation. What are you going to find? Well, if you go in momentum space and you look at the beta function, you will find a non-perturbative theory, and this presumably means you will find confinement, because you're going to have NC squared loops, NF times NC quark loops, NC squared gluon loops give you anti-screening, NF and C quark give you screening. Therefore, anti-screening still dominates, provided that you've taken the NC limit, large NC rather than the large NF limit. Scale is color independent, so you set it up at the Planck scale, it's color independent, so at the large NC limit, in this mu bar equals n bar, in this limit, in momentum space, you're going to have a non-perturbative theory, and probably it's confining. However, now you go into configuration space, you realize that the interquark distance is 1 over NC, which you've taken to infinity, 1 over NC to the 1/3. And that goes to 0, because NC goes to infinity. And therefore, you have a situation where you have PQCD in configuration space and confinement in momentum space. What the hell is going on? This was the paper by Larry and Rob in 2007, and independently from what happens afterwards, it asks a very, very, very interesting question, because this is an issue that sort of, on a conceptual level, is very interesting. Their idea of what's going on is that their potential answer of what's going on is that over here, you have a new phase called quarkyonic matter, where essentially baryons are still, where essentially the Fermi surface is quark-like. So dynamics of the Fermi surface is controlled by PQCD. However, baryons still exist as potential objects. Confinement is still there. And any excitation, which is shorter wavelength of the baryon size, will be colorless, i.e. it will be another baryon. So you have a coexistence of equilibrated perturbative quarks in the ultraviolet and baryons, colorless baryons in the infrared. Since at large NC baryons are also, as Witten showed us, semi-classical objects, you can actually sort of intuitively imagine this to be something like a conductor. I mean, in a conductor, you have an electron Fermi surface of free electrons, and atoms look like potential wells. So it's something similar. Instead of baryons instead of atoms and quarks instead of electrons. So this was the idea. Since then, an enormous amount of work has gone into it. There have been several. It has been one frustrating aspect of this work is that every single author started defining quarkyonic matter in their own possible way, because if you look at every paper about quarkyonic matter, they mean something different. I'll stick to the original definition here, and this is the idea. So this would be something really exciting that FAIR, for example, could look for, even if there is no critical point. There is no critical point, we're going to look for quarkyonic matter. Perfect. Or not. Because the approximation of 3 equals infinity and a third equals 0 is something that not everyone is comfortable with. Now, the reason is, and I'm not being facetious here, the problem is that the large NC approximation in QCD on a qualitative level works really well for certain things. I mean, the Aussie rule that people mentioned in their talks yesterday, the SCRM model, planar diagrams, all this stuff seems to work qualitatively well as it should. However, there are some predictions from the large NC limit which are spectacularly wrong. At large NC, the nuclear binding energy, at large NC, the nuclear binding energy is of the order of the nucleon mass. As any low-energy nuclear physicist knows here, you've gotten it wrong by like 3 orders of magnitude. And in fact, I would say that this is sort of mysterious. This is a hierarchy problem like the cosmological constant or something like this. Why should the nuclear binding energy be parametrically smaller than the pion mass, which in effective theories people generally treat as massless? You know, the pion mass being small, the pion mass is what in QCD is called masslessness, and here you have a nuclear binding energy which is smaller by a factor of 10 to 100, where in the large NC approximation, which qualitatively should work, it's of the order of 1 GeV. There is also other things which derive from this. I mean, the spin flip energy, the energy to make a spin flip, so the delta baryon difference is also parametrically very small in large N, and it's large in QCD. The ground state is completely different, et cetera, et cetera, et cetera. So what's going on? Well, a possible answer that we gave was that there is a phase transition, there is an extra phase transition in the space of the number of colors. This is not something you're likely to find at FAIR, although if you can manage to investigate this, I'll be really impressed. That basically the number of colors is not a continuum. The number of colors is not a continuum, that isn't approached continuously, because of the fact that dense matter, a tightly packed system of spheres, in addition to the number of colors, also has another dimensionless scale, which is the number of neighbors. And the true large number of colors limit is when the number of colors is much bigger than the number of neighbors, namely 10 or so. Why? Because in this limit, it is possible to rotate in color space every baryon in a different direction and not eliminate any problem with the Pauli exclusion principle. In this limit, you cannot do it. And therefore, in this limit, baryons, at least at high density, are still deeply quantum objects which obey the Pauli exclusion principle. You have to rearrange the quarks, and that changes the quark energy. In this limit, you don't. We found using some admittedly toy models for the quark for propagators between quarks, we actually found a percolation phase transition where the quark states remain localized in every baryon, below the percolation phase transition and above the percolation phase transition, the quark wave function of different baryons becomes entangled, and the correlation length stretches to infinity. It's the same percolation transition that you find in percolation toy models you learn at university, and the probability of a quark propagating a certain distance, the probability of two quarks interacting will go as 1 over NC in such a way that the critical number of colors for percolation is about the same as the number of neighbors, which is really not surprising because that's what happens. That's intuitively what happens. Intuitively, if you correlate two quarks from two different baryons interact below the percolation phase transition, this changes only these two quarks. Above the percolation phase transition, you start having chains forming, which are of arbitrary length. That's what percolation is. Since we don't live in a universe where the number of colors is 10, we could then say, and since a common wave function among all quarks is the assumption you are making for the existence of quarkyonic matter, we might be able to conclude that quarkyonic matter exists, but only in our minds, because that's where SU10 theories reside. However, if we actually include both density variation and number of colors variation, unsurprisingly, we find a curvature on this phase transition line between number of colors and critical density. And it turns out that a small sliver of quarkyonic matter, once you do this carefully, a small sliver of quarkyonic matter is still allowed. It very much depends on whether you consider the number of light quarks 2 or 3, which, of course, the strange quark is in between, and this becomes an issue. But basically, the idea is there is a percolation phase transition if you keep the chemical potential constant. If you keep the chemical potential constant in such a way as that there is a baryon per baryon size, there is a baryon per baryon size. Remember that at deconfinement, you need roughly NC baryons per baryon size. If you keep a baryon per baryon size, you need the number of colors isn't enough to create a Fermi sphere of super baryonic size. Quark interactions are local. You need number of colors of 10 or more to produce something like quarkyonic matter. But if you allow more than 1 baryon per baryon size, then it might be possible for percolation to occur at NC equals 3. Or not. I mean, you're kind of stretching it, but it's not impossible. Which basically means that one can try doing phenomenology. One can try doing phenomenology without, like, being slightly optimistic, but not being super optimistic. So how do you do phenomenology? You can try to vary NC on the lattice at finite chemical potential. When I was last giving talks about this stuff, as you see, the papers are from something like 2013, so I stopped giving these talks in 2014 or so. I basically put up this slide here because essentially lattice theorists, when I was describing them this issue and saying, you should vary NC and also put in a baryon and do it finite chemical potential, the lattice people were saying, yeah, sure, of course. That's easy. However, we're in 2019 now, and Uwe Philipsen and collaborators have put out the first paper where they investigate the nuclear liquid gas phase transition at varying NC. They didn't really find the phase transition in NC space yet. It's the first paper, and in a sense, it's a toy model because it's in the strong coupling approximation, and for example, it doesn't have the sign problem. But I'm just saying, this used to be the case, but this is becoming an active work, and it's very nice to know, and maybe in the next 3 or 4 whatever years, we will find out if there is an interesting structure in NC space from pure gauge theory using numerical methods. How much time do I have? 11, thank you. Yeah. one can do, quarkyonic matter might have, and this is something that Larry McLaren has been exploring recently, quarkyonic matter might have non-trivial consequences in neutron stars and particularly supernova explosions. Because if it exists, it's a very non-trivial phase transition. It's not really a phase transition from statistical mechanics terms because the energy density doesn't jump, but the pressure jumps. Because you go from a baryonic Fermi surface to a quark Fermi surface. And this basically means that the energy density changes very little, the pressure changes a lot, but you don't have any first order phase transition. You don't have a mixed phase. For proton-neutron stars during a type 2 supernova explosion, this could have very profound consequences. And there is work to be done, and there is work to be done in this direction. So this might have astrophysical consequences. Finally, thank you. There is a probe which might directly be sensitive to quarkyonic matter, which is direct photons. The reason is the following. I mean, let's go back to basics and let's revisit our definition. So in our definition, the system is composed of baryons, but these baryons essentially are the infrared degrees of freedom. They behave as classical potential wells, and inside them you have quarks which have a Fermi surface which is common to all baryons. What this means is that there will be a direct photon contribution which will come from the quarks, not from the baryons. However, the form factor of the quarks will not be the form factor of one baryon, it will be the form factor of the whole system. And this is something that we can calculate relatively easily. I mean, we basically take PQCD, the photon to quark coupling, and we plug in a form factor here, which is essentially the Fourier transform of your baryon configuration into the system that you get from your RQMD or URQMD or something like that. Again, this is nice because the very nice physical analogy of this, which I think is really helpful, is the valence gap in the conduction band, the valence band and the conduction band in electrons. In a conductor, electrons are a Fermi, in a metal, sorry, electrons are a Fermi surface, but you still see atoms as classical potentials. This is exactly what the role of baryons is in quarkyonic matter. They are the slow degrees of freedom. The fast degrees of freedom are perturbative quarks which are in equilibrium, but their configuration is given by the baryons. So this is basically what we did. We ran our QMD to get a dense gas of baryons and see how it evolves. We used the potential to construct a guiding, to construct wave packets, to construct an envelope function and put quark wave functions into the envelope function. And then we used PQCD cross sections to calculate to calculate the direct photon spectra. This is the matrix element. Bremsstrahlung dominates. The calculation is done exactly like in a quark gluon plasma. The only difference is we put in the form factors which are given by the RQMD thing. And then we calculate the spectrum and we calculate V2. The difference is, as I said, the hadron gas background is simply hadrons will interact and decay and some photons will be emitted. In a quark gluon plasma, you will have this matrix element, but the wave function will be the thermal quark wave. The wave function for the quarks will be the thermal quark wave function. In quarkyonic matter, it will be the form factor. The essential result is that the quarkyonic spectrum of photons, is very similar to the quark gluon plasma spectrum of photons at the same temperature. However, the Quarkyonic V2 is a complete mess because the fact that quarks are confined in baryons, and baryons have a non-trivial configuration, and quarks are a coherent superposition of these baryons, which are located in random positions in space, essentially means that V2 loses any dependence of the eccentricity. Its average by momentum beam is going to be 0, but it will also oscillate with momentum chaotically. If you can do V2 fluctuations at this energy, the photon V2 fluctuations at this energy, they're going to be huge. Of course, no one can measure photon V2 fluctuations in heavy ion collisions, but in any case, the idea is that you will have spectra comparable to a quark-gluon plasma, but any collective flow photons is not going to be there because of the fact that photon wave functions will reflect the space-time configuration of the baryons, and this introduces chaos. At the time, we were thinking that this could be developed further into a dilepton calculation because the space-time structure of the diquark wave function would show up in the invariant mass distribution of the dileptons. Dileptons will not just have V2 or anything else, they will also have the invariant mass distribution in a quarkyonic scenario, basically, just like you have a metal insulator phase transition, you have a metal insulator gap. In quarkyonic matter, you might have a gap which distinguishes interbaryon distance from a baryon, and this will show up in the dilepton mass distribution. We did not develop this. This would be one obvious thing to develop if we come back to doing this stuff. But the whole point is that electromagnetic signatures will be if quarkyonic matter exists, and if quarkyonic matter has the properties that Maclaurin and Pisarski says it has, electromagnetic signatures are the things to look for because quark wave functions will be non-trivial because they will reflect the distribution of the baryons. And this could be seen in photon spectra and eventually in dilepton mass distributions. And this is the last thing to say. My conclusions are basically that I think that physics at low energy is really interesting because there might be theoretical surprises, there might be things that people do not see, that people haven't thought about. Quarkyonic matter might or might not exist. It might only exist at large NC, or it might exist in the physical world. We do not know. What it is the idea that in the large NC limit, the quark and the baryon separate so that quarks become perturbative, but baryons exist is compelling. It's not clear if NC is large enough for that to happen. Electromagnetic signals are the only promising observable I can think of, and there is certainly a lot of work to do. Not really sure what this is. Yeah, these are the conferences Bruno is going to organize on some beach in São Paulo dealing with this matter.
Thank you very much.
Thank you.
Comments or question?
Maybe I missed something in the very beginning. Is there a dynamical symmetry breaking in this phase, in this quarkyonic phase?
I believe so, yeah, because it's perturbative.
Perturbative?
Well, wait a second. That's a very good question, because that is a very, very good question, because quarks become perturbative, and perturbative quarks are massless. However, a remnant of the Kasher's argument should exist. I mean, Kasher's argument basically is a fancy way of saying if you put a massless particle in a box, it will acquire a mass which is about the size of the box. Here you don't have a box because you have many baryons and they go across, distances. However, you have a form factor because these baryons form a potential well. And this form factor you can think of as a momentum-dependent mass. But the momentum dependence is very non-trivial because it reflects the macroscopic baryon configuration. And causality, there is a way to do this in a causal fashion. So there is no constituent quark mass, if that's what you mean. But the form factor could occasionally behave as a mass. I think that in the long paper we put a qualitative discussion about this. I think that what's going to happen is that if you look at the invariant mass spectrum of dileptons, you're going to have a gap. Because in the interbaryon separation, you will not have any quark states. And this is the significance of the form factor. Sure. Yeah, so that will not exist. Well, the form factor comes from the baryonic wave function, which is not a perturbative effect.
Okay.
So you said that quarkyonic matter might have astrophysical consequences, and you said that quarkyonic matter might have astrophysical consequences, and I would like to ask you if you believe that gravitational waves and LIGO are necessary or sufficient for saying that whether neutron stars have quarkyonic matter by constraining the equations of state, or if it's required more to say that they really exist.
So one of the originators of the quarkyonic idea, Larry McLaren, is convinced that gravitational waves have proven quarkyonic matter. And he wrote a paper about this year. There is a paper on arXiv about this year, and he basically says that this jump in pressure is required by LIGO. I am not familiar with these arguments, so I do not know.
You have to be careful a little bit, right? So, just now there was a paper published where they compared the equation of state of something that had some form of deconfined quark matter, not quarkyonic, and something that only contained hadrons, right? And they were able to see through very detailed general relativistic simulations that there are some differences in the pattern of the emission of gravitational waves. So this is a paper published just a month ago. So I think it would be better to trust a real calculation instead of just some jump somewhere done, out of the blue. But my point is the following. So one, you have to distinguish from an argument that may be valid in large its limit from a real calculation based on QCD, at least, or something else at large N that actually supports the evidence for quarkyonic. So I don't think such a thing exists. So that's number one. And number two, so that's actually a question. What is the typical scale and chemical potential where you expect the onset of quarkyonic matter, if it exists, to show up?
The baryochemical potential will be the same as the baryon mass.
Okay, on the temperature?
The temperature is going to be about from 0 to Tc. To the curvature of at least in the large NC limit,
Okay, I want a number.
That's
a number.
good
I don't want
point.
tildes.
Yeah.
No squiggles.
Okay, so temperature lower than Tc, chemical potential the same as the baryon mass.
So Tc is a what, 155?
Yeah.
Okay.
Okay. We can discuss, but...
Well, is it 155 or 170?
Today, no, Harris.
Okay.
Yeah. But I think what you meant is the chemical potential of the baryon and the critical temperature at that chemical potential, right?
I meant critical temperature at 0 chemical potential, actually. Because the curvature...
But this is not where you see quarkyonic matter, right?
Yeah, we don't see quarkyonic.
No, the idea is, okay, this is Tc.
Yeah.
This is mu b.
Yeah.
at infinite number of colors, at infinite number of colors, this is mu b equals mb.
Sure. But now we're talking about the real world,
At infinite number of colors,
right?
this is what the phase diagram looks like. There is no curvature here, and this guy here is a vertical line.
But in the real world, we have some curvature, right?
Sure.
No.
So in the real world, people usually say it's something like this.
So any number between 0 and 155.
Yeah.
That sounds very predictable.
Yeah. Well, I mean, unless people see a spectacular signature of this stuff, I think no one will believe it.
And
I mean,
your critical chemical potential here, mu baryon, is probably to the left of the chiral restoration line. What happens then?
sorry?
Your mu baryon, right, that you have here, this is basically the chemical potential where you have the liquid-gas transition, right?
Yeah.
And that liquid-gas transition line is left of the
That is
chiral
true.
restoration line.
That
So
is true.
this is not, your dashed line would then be to the left of the solid line.
To the
And then-
left.
Yes. And then there's not much space for
You're saying that this is the liquid gas?
this would be the liquid gas,
Yes.
yes. And the curvature of the transition line is very, very narrow, very, very close to this dashed line. So if what you say is true, that the quarkyonic phase is between these two, there's not much space in between, actually.
I agree. And in fact, in the first paper we wrote about this stuff, which is the STUN 006, we made the argument that quarkyonic matter is the liquid-gas phase transition at large NC. That basically liquid gas will look like quarkyonic matter at large NC. Yeah. The question, I think to answer the question you're asking, one has to ask what happens to chiral symmetry. And I would say what happens to chiral symmetry, and we go back to the earlier question, and I actually think that that there is no trivial answer to this. I mean, there is no, quarkyonic matter has no chiral condensate in the, quarkyonic matter has no chiral condensate in the traditional phase, which is a Lorentz scalar, et cetera, because the baryon structure breaks all kinds of symmetries, Lorentz symmetry, translation symmetry, et cetera. So the chiral condensate will strongly depend on momentum.
Then there are inhomogeneous phases all over the place, and it breaks loose.
And
right?
I think that in this sense, the chiral transition line is sort of an iffy question. You see what I mean?
Okay, we should stop now and discuss after this. Next talk is Marina. Nice discussion we had. Then next talk is Marina Nielsen from USP. Title is Recent Developments on the X, Y, and Z States.
I can speak without mic. Can I? You can't hear me. No, you can. Because I saw that. They're recording. They are recording. So I cannot. Where do I put it? They don't have pockets. They don't have anything here. There is a regular. Let's see if it goes here. If it goes here, it's okay. Yeah. This is not prepared for a woman. Yeah. I think it worked. Okay. So thank you, the organizers, for giving me the opportunity to talk about this subject here. It's based on this recent review done with these collaborators here. So if we ask about how many are these new X, Y, and Z states observed in last years, there is a table here, and this is not all. This is only the beginning of the table. And we can see they are organized by the mass. So this is, it's not the year that was observed, but the mass. Here is the mass, the width, the quantum numbers when they are known. This is the process where they were seen, and these are the experiments. The red one was the collaboration that saw the state for the first time, and the blue one is a non-confirmation of the observation. The X was the first one observed. It was in 2003, and this charged state one, it's the last one that was observed last year, at the end of the last year. So you see, we have 15 years of observation for these states. The list goes on, and here again, this is the first observation, a non-confirmation. And this state was the first charged one that was observed by Bell collaboration in 2007. And this was a really big thing, because if it's in the charmonium mass range, but it's charged, so it cannot be a CC bar state. So it has to be or a molecular or a tetraquark state. And this was really exciting at the time, until Babar collaboration only 2 years after, searched for this state in 4 different modes and didn't see any evidence for the existence of this state. So this was really bad for the community. Everybody was excited, and then we were not excited anymore. We didn't know what's happening. And this was like that until 2013. But here you see it's again Bell collaboration that confirmed the observation of the state that they saw before. It was the same collaboration. They have a higher statistics. Also, they have a calculation information for the quantum numbers of the state. But since it was the same collaboration, nobody was so excited again about that. Only in 2004, LHSB has confirmed the observation of this state, and also with a higher statistic, and also confirming the quantum numbers that Bell had proposed. And these are the mass and width of the state that we can see if you look at the PDG now. And this is the observation, experimental data for this state. But LHSB did more than that. They also did the first attempt to see the resonant character of this state. What they did was they changed the bright Wegener amplitude by 6 different amplitudes, independent amplitudes in this psi prime pi mass spectrum all over the mass of the Z. And what they saw in this Argand diagram is consistent with a rapid phase transition that's expected from a resonance. So this was really the first time that this collaboration did an analysis that confirmed the existence of a resonance. So this was the end of this point. Now everybody believes in the existence of this charged state. So here is the theoretical, what happened in the theoretical side of this state here. So we have here 2 lines, and you can see here, all this is before the LHSB data, and this is after. Here we have different quantum numbers for this state because it was not determined. So the theoretician was supposing some quantum numbers. There are even 2 calculations here that said that this would not be a real state, just a cusp in D1 D star channel or a threshold effect. And there is also this proposition here that has the correct quantum numbers for this state. As I said, this was before, when we have different quantum numbers for the state, and after LHSB, when all the propositions have the correct quantum numbers for the state that was already observed. This explanation by Miami collaboration is very interesting, because when the X was observed, they did a quark model analysis for tetraquark states with the same content of the X. And they found lots of tetraquark possible states. One was a charged one that has a mass very similar to the X and should decay in J psi pi. So when the Z was observed, they saw that the mass was not compatible with that. It's 506 MeV above the mass of the predicted state here. And also, they saw that this state decays in psi prime pi, not J psi pi. Comparing the mass difference between here and the psi prime in J psi, we see that it's almost the same mass difference. So this is what led them to propose the Z as being the first radial excitation of this state that they were predicting in their calculation. And indeed, this state was observed some years after, in 2013, by Bell's collaboration, also almost at the same time by Bell collaboration. So in this sense, I think that this is a very good explanation for the mass of this state, for the structure of this state here, since everything is compatible here. So now I will talk about these charged harmonic states that were discovered in 2013. So this is C3900 is the first one, and it was saw in the decay of this other Y state here. This is the peak that was observed. And soon after that, the same collaboration, the S3, saw another charged state with a mass very similar to that mass, but decaying another channel here. And this is the signal here. So the first question that we could say is, could these two states could be the same state? If we compare just the mass and the width, we see that they could be the same state. And this is what Bess did. They supposed that these two states were the same, and they were able to evaluate this branching ratio between these two decay modes here. If we look at PDG, at the beginning they were two different states, but if you look at PDG now, they also put these two states as the same one. So this was it was called the 3900, and this is 3885. When they were discovered, they were supposed to be two different states, but now PDG classified them as the same state. And what about theoretical calculations about this state? So we did a theoretical calculation using QCD São rules for these charged states, and we evaluated the mass and also the decay width in different channels here, as you can say. If you add all these decay widths, the total width is compatible with the total width of the Z. However, if we calculate these branching ratios between these two decay modes, DD star and J psi pi, we have this number here. And this is, considering the errors, the same result as Mayan and collaborators obtained using their quark model, tetraquark model. And this is not compatible with the result from BESS2 if they compare the mass of these two charged states. So what we can say is that from a QCD São rules and tetraquark model point of view, these are not the same states. So we have a problem to solve yet here. Okay, up to now, we have 8 harmonium charged states that are put here. So when we have a non-confirmation for these states, in these 1, 2, 3, 4 cases here, we have only one observation. There is no confirmation. This is the last one that was observed only with 3 sigma. So this state really needs a confirmation. We can also see here that the mass of these states are also very similar. And if you look to PDG now, to the mass and the width, we see that considering the uncertainties here, even the width are compatible with one another. So they could also say that this could be the same state only observed in these 2 different channel models, but they don't say anything about that. So this was a Bell observation in 2014. And for this state, there was observation and a non-confirmation, blah, blah, blah. And when this state was observed by Bell, they didn't say anything about the other. Although in the other case, they said that they could be the same state. Okay, so this is what I have to tell you about the charged states. And now I go on, and, okay, there is one more thing. We know we have explanation for this state, these two here, and we have also some explanation for this state here, but we don't have explanations for any of the other states here. So we still need theoretical explanation because there are too many charged states here to be accommodated with any model. And now I go to the Y family. The Y family, it's called, now it's not the name that PGG gives to this state. It calls SAIFR, all of them. But then we don't know why a psi is a tetraquark or 4-quark state or it's a QQ bar. So I keep the original name for these states. And the states that has these quantum numbers, 1 minus minus, are called Y states. And we have here all of them. This was the first one observed in 2005, and this was the last one observed in 2017. So as you can see, lots of these states are still being observed. So let's start with the first three states that they were observed in this E plus, E minus to 1 minus minus final states via initial state radiation. Because in these B factors, the energy of the E plus, E minus were much higher than the Y state. So there is this first initial radiation state, and then the virtual photon here has the mass compatible with the observation. So the first one was the Y4260 that was observed in J psi pi plus pi minus, and the other two observed in 2007 by Bell in the channel psi prime pi plus pi minus. And here I put the mass in the first observation, and here the mass that you can find at PDG. And we can see that there are some difference in this. And the first question is, why are these states exotics? Why cannot be just CC bar normal states, vector states? The point is that the mass and widths of these states are not consistent with any 1 minus minus harmonic states that we can, using quark models, evaluate the mass and decay of all 1 minus minus states, and we can see that these three states goes exactly in between the theoretical calculations for the CC bar states. Also, for one explanation should be that Y could be a harmonium hybrid with a gluon here. But if you look at LATSI calculations and string model calculations, we see that the mass is much higher than the observed mass. Although in this flux tube mode, the mass is compatible. But there are other problems. If it was a harmonium hybrid, there is a calculation here that shows that dominant decay mode should be in mesons, not in J psi pi plus pi minus, D mesons. There is this calculation by Mayan and collaborators that suppose that it could be a 1 minus minus tetraquark state, but a strange content here. Although there is a theoretical calculation that say that such a state would have a much higher mass than 4260. There are other possible explanations for this state, like a baryonium, S-wave threshold, molecular state, manifestation of reg zeros. And all these three states, in particular the Y42, it was first observed by B factors with limited statistics. And now BEST3 is investigating these states again, and they have much higher statistics. So you can ask what they are seeing. And so here I put what we know about the Y4260. This is the mass and width for the first approximation, and this is the mass and width if you look at PDG now. Here it's the first observation for the Y by BEST3. This was done in 2014, and they observed this state in this decay channel here. And the mass that I observed and the decay width are this one. And they said this is not consistent with 4260. This is what they say in their experimental paper. This was in 2014. Now, in 2016, they did another experiment in this other channel here, and they saw two different resonances. These are the mass and widths for these resonances. And they also say that the two of them are inconsistent with 4260 and 4060. Although the mass are similar, they said they are not consistent. But the smaller mass here resonance, they say that it's consistent with the state saw in this decay channel here. And they call this higher mass state, they gave another name for this higher mass state. What they mean when they say they are not consistent. So this is what they do. They do this analysis here in the width and this mass and width plane. And this is the state that they are observing. And this is the 4260. And here it's the other one, and this is the 4360. So this is why they say that they are not compatible with the other ones, because they have this kind of investigating everything in this mass and width plane here. Okay, we go on, and in 2016, they did another analysis in this other decay channel. And remember, this is the decay channel that the Y4260 was first observed. They saw two resonances here. The mass are this one. And in this case, they say that they are consistent with the 4260 and 4360. And this is the first time that this state would be observed in this channel here. In 2017, they did the same, another analysis in this other channel here, and this was the channel that the 4360 was first observed. And here they also see two resonances, but now they say that they are not consistent with 4260 and 4360, but they are consistent with the other two that were observed in this other decay channel. And finally, in 2018, they looked to this channel here, and they also saw two resonances, this mass in analysis, and they say that the lower mass is in a good agreement with the 42.2, not 42.6. After all this analysis, at the end of this paper here, what they say is that BES3, they indicated that this structure that we call the 42.6, as a matter of fact, consists of two resonances, 4220 and 4320. So this is something that is still there on debate, because this appeared, as you can see, it's very recent. It's from August of last year. So this is something that the community has first to solve and tell us if it's really 4 states, 2 states, 1 state is 2, or 2 states 1. I don't know what to think anymore. What we can do is calculations. And we did a calculation for this state, and we considered, first we considered the same current that Marianne was proposed. And what we got is a mass that's not consistent with the 4260, but with the 4660. We did also other calculations considering a molecular state, and we also get a mass that's not compatible. And we did even other currents. You can see the mass here. What we can say is none of the currents that we have used are consistent with the mass of the 42.6. Based on that, we decided to do a mixed current to evaluate this state. So we are mixed of tetraquark and a normal Chorionic state here. And in this case, for this angle here, we got a mass that's consistent with the mass of the state. We also did a calculation for the, for the width. And we got a width that's much smaller than the experimental width. So this could be an indication that the J psi pi is not pi plus pi minus, is not the main decay channel of this state here, and the main decay channel could be in these states. In this case, maybe this 4220 that was saw in the star decay mode could be really the main important part of the 4260. We also did the calculation for the production, and in this case, we get a number that's compatible with the experimental upper limit. And now I will talk about the X. the X was the most studied state that we have since it was discovered. It was confirmed by all the collaborations that tried to see the state, saw this state, so there is no doubt about the existence of this state. There is no doubt about the quantum number of the state. So, and what we can say is that why it's exotic, because if you look again to the quark-anti-quark calculations for these 1++ states, we see that the mass is not compatible with neither of the states that could be near to the mass of this state. Also, there is this experimental evidence here of a strong isospin impurity violation, since it's the case in J psi pi 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 and J psi pi pi. Also, since the mass of the D star D is so close to the mass of the X, there was this proposition that the X could be a D star molecular state. The difference between a tetraquark that was proposed by Mayani and a molecular state here is only the way that the quarks are organized inside the state. A tetraquark would be a very compact state, and a molecular state would be a bigger state. If we look at the production of the X, it can be producing B factors to the B decay here. And there are calculations based on mesomolecular or tetraquark. And in both cases, we can explain the production rate of the X in B decays without problem. So each one of the models are okay. There is no problem with that. However, there is another way of producing the X that's from proton-proton or proton-to-proton collisions that was solved by this collaboration here. And CMS has even measured the cross-section for the production of the B in this PP collision. But look at that. If I have a PP, high-energy collision here, to form a molecular state, a loosely bound molecular state, it seems very difficult to believe that we could form a loosely bound molecular state for a high-energy PP collision, because this should be formed through gluon formation here with the C. And indeed, the first theoretical estimates for a molecular production, molecular structure for the X production in these collisions give a cross-section that 300 times smaller than the experimental one. However, there are other theoretical calculations that use another ingredients, and they can say that even in this case, we can find a cross-section that's compatible with the experimental one for a molecular state, in this case here. There is also a calculation for the tetraquark. In this case, it's not very difficult. And here we can see that this calculation can put it's compatible with the observed one, although there is parameters in the model that can be fixed to reproduce the experimental number. But what is interesting is from this measurement here, and these are the Atlas data for the X production, prompt production in PP collisions. And we can see that here that the data can be very well explained by this non-relativistic calculation here using next leading order. However, to be able to do this calculation, what they are supposing is the X is not only a molecular state, but it's a mixture between a normal CC bar state and a molecular state. So these are the theoretical calculations are based in this paper. So we also did this. We did a QCD some rules calculation for the X. First, we suppose that this was just a tetraquark state, and we get a mass compatible with the state. But we cannot get a decay width compatible with the state. So the decay width that we get for just a tetraquark state is much bigger than the experimental width. But if you use, again, a mixture between a tetraquark and a two-quark state here with this kind of currents, we can get a mass compatible with the state and also a decay width that's also compatible with the state with exactly the same mixing angle here in the two calculations. And we can do more than that. We can, here it's We can calculate the decay width of the X in J psi gamma, and this is the experimental measurement. This is the result of our calculation with exactly the same angle. And also the production of the X through B decays. And using the same angle, this is the number that we get that's compatible with the experimental upper limit. So what we can say is that from a QCD sum rule calculation, the X is probably a mixture between a 2-quark state and a tetraquark state as the calculation that Atlas used to explain their data. So now I arrive at my conclusions. What we can say about the X is probably it's a mixture between a 4 state and a CC bar state. DZ plus probably is a tetraquark state, DZ 3900. And the ZC 40-40-30 is the first radial excitation of this state here. The Z plus states of the charged harmonic states needs confirmation, of course, because there are too many of them. And we should know that just a bump in the spectra, it's not necessarily an indication of the existence of a state. The Y4260 is probably also a mixture between a harmonium and a 4-quark state. And for the 4660, it's, in our calculations, compatible with a CS, C bar, S bar state. Remember that this is a problem still in the experimental side because there are 2 states here that maybe it's the same and maybe it's not, but the experimentalists have to decide about this state first. And that's all. Thank you.
Thank you very much for the nice talk. We have still enough time for discussions and questions. Questions? Comments? Nope. Seems the talk was pretty.
Marina, I mean, this is very nice that you can compose these heavy mesons as mixtures, but can you see some kind of systematic? Because it looks that is each one by each one, but there is some kind, because QCD should have in some way some systematic. Can you see that?
Yeah, what we are thinking now is that if it's possible to have a mixture, it will have. The difference will be the angle. Maybe some states has the biggest part of them is the tetraquark. The most important part is the tetraquark. Other ones, the most important part is the 2-quark state. But if it's possible to have a mixture, it will have. So the mixture will only not be possible in the charged states. All other states probably are a mixture of the tetraquark and harmonium states.
So you can even have hepta and so on. Well, this looks like that you can add light hepta. So you have 2, 4, 6.
Yes, we could, but they should be less important. Yeah, they should be less important.
Other comments, questions? Then thank you very much again and thank you very much for all of the speakers today.